Welcome to the deep dive.
Great to be here.
So AI is absolutely everywhere, right? And the headlines, they often focus on, the latest breakthrough or the flashiest new algorithm.
Oh, definitely. The hype is real.
But beneath all that hype, what truly separates the successful AI solutions? The ones that actually deliver real tangible value from the ones that just, fizzle out.
Yeah, that's the key question.
And it's often not the algorithms themselves, surprisingly. Today, we're taking a deep dive into that practical end-to-end journey of building truly impactful AI solutions.
And to ground us in reality, we're going to walk through a really compelling real-world example, building a real-time credit card fraud detection system.
Exactly. This isn't just about the model. It's about understanding the entire life cycle, soup to nuts.
That's absolutely right. And what's often overlooked but is really fascinating here is that to de-risk these complex projects and truly deliver value, there's this methodical four-phase journey we're going to unpack for you.
4 phases. Okay.
Yeah, it kicks off with the blueprint, then moves into the build. After that comes the deployment, and crucially, the feedback loop.
The feedback loop. Right?
And this structured approach, well, it's precisely what transforms an abstract idea into a tangible, high-impact AI system. It takes the guesswork out.
Indeed. So our mission for you today is basically to give you a shortcut, right? A way to get incredibly well informed about this entire process. We're going to reveal some surprising facts and crucial insights that turn these abstract AI concepts into actionable knowledge.
Hopefully. Yeah.
By the end of this deep dive, you'll have that strategic framework. You'll understand exactly how any AI project goes from just a concept to a deployed, value-generating system.
That's the goal.
So let's start right at the very beginning. Before we even think about code or algorithms, the groundwork has to be absolutely solid. What's the very first, maybe even counterintuitive step in laying that foundation?
It's what we call the blueprint phase. And the absolute first, most crucial step. It's a deep, structured, and frankly, rigorous understanding of the problem itself.
Okay, understanding the problem. Sounds simple, but I bet it's not.
It's surprisingly complex, yeah.
Yeah.
This initial phase is so vital because it fundamentally de-risks the project. It's not just planning. It's about preventing the biggest reason AI projects fail.
Which is?
Building the perfect solution to the wrong problem.
Ah, right. I see.
So this phase ensures that all the technical effort, all the coding, aligns directly with the core business objectives. And crucially, it helps identify potential roadblocks really early on.
Which prevents a ton of wasted effort later.
Exactly. A tremendous amount.
So how do you actually do that? How do you take a general business goal, something like reduce fraud losses, and translate it into something precise and AI can actually act on? What does problem framing really involve day to day?
Well, problem framing is a highly collaborative process. It really starts with the why.
The why.
Yeah. For a fraud detection system, the why is pretty clear. Mitigate financial risk, sure, but also preserve customer trust. That's huge.
Okay.
So you articulate clear objectives, and then you have to decompose those, break down the abstract needs into specific, actionable questions an AI could potentially answer.
And who's involved in that conversation? It can't just be the tech folks.
Absolutely not. It involves engaging diverse key stakeholders. You've got your business sponsor, maybe the head of risk who owns the goal. Then your domain experts, the fraud analysts on the ground who really understand the fraud patterns.
The ones who see it every day.
Precisely. And of course, data scientists, IT, operations for the technical side. And don't forget, legal and compliance. Very important for fraud.
Yeah, regulations and all that.
Exactly. And you need to ask specific questions like, okay, if we detect potential fraud, what happens? Do we block the transaction? Do we flag it for review?
Right, the actual action.
Or what's the acceptable latency? How fast does this prediction need to happen? Milliseconds matter in real-time fraud.
I've heard about a tool for this, the problem framing canvas. Sounds useful. How does that actually help structure the discussion?
Oh, the problem framing canvas is brilliant. It systematically structures this exact conversation, making sure you don't miss anything crucial.
Like a checklist.
Sort of, but more dynamic. For our fraud system, it would document the precise business goal, like reduce direct financial losses from fraudulent credit card transactions by 15% within the first year. Very specific.
Okay, measurable.
Then you define the AI problem. In this case, it's a binary classification model. Is it fraud or not? Predicting the probability.
Right.
You outline the ideal outcome, list the stakeholders we just talked about, nail down critical constraints like P99 latency must be under 150 milliseconds or must be GDPR compliant.
Technical and legal constraints, got it.
And clearly list the data sources.
Right.
Historical transaction logs, crucially, with reliable fraud labels and the real-time transaction stream itself.
So it takes this vague need and turns it into a really well-defined technical challenge.
Exactly. And it aligns everyone, from the head of risk right through to the legal team. Everyone's on the same page.
Okay, so we've framed the problem meticulously. Now, how do you figure out if you can even build this thing? Or, maybe more importantly, if you should?
That brings us to the critical feasibility study. It's got a dual purpose, really.
Okay.
First, assessing, can we build this? That's about data and technical readiness. Second, should we build this? Which is all about the business value.
Let's break that down. Data readiness.
Data readiness is paramount. AI systems are fundamentally data dependent, right? Garbage in, garbage out.
A classic saying.
It really holds true. So you need to assess not just availability. Do we have historical transaction data with reliable fraud labels? That's often a big hurdle.
Reliable labels, yeah.
But also its quality. Is it complete, accurate, consistent? And crucially, are there potential biases lurking in the data that could skew our model? Big ethical implications there too.
Definitely. And the technical side of feasibility.
Right. Technical feasibility. That involves evaluating your infrastructure. Do you have the computational horsepower, like cloud GPUs for training, and the scalable compute needed for real-time predictions?
Millions of transactions potentially.
Exactly. Are there suitable algorithms and tools available? For fraud, as I mentioned, something like LightGBM is a fantastic choice. It's incredibly fast, efficient on these big tabular data sets, and gives great accuracy. Vital for real-time stuff.
Makes sense.
And maybe most importantly, do you have the right team? A multidisciplinary team with skills across data science, ML engineering, MLOps. You need that whole spectrum to get from A to Z.
It's definitely a team sport.
Absolutely. We often use a tool like a value versus feasibility matrix to help prioritize projects.
How does that work?
It's simple, just a quadrant chart.
Yeah.
You plot projects based on potential business value and technical feasibility. A real-time fraud detection system, that falls squarely into the rockets quadrant.
Rockets meaning?
High value, huge financial impact, protects customers, and high feasibility, given today's tech. It's the kind of project you absolutely want to launch. Go for it.
Okay, that matrix sounds useful. Now, this idea of measuring success really interests me. For something high stakes like fraud, what are the common mistakes companies make in measuring performance? Because I heard, and this is really interesting, that standard accuracy is actually dangerous here.
You've hit on a critical point. Yes, for highly imbalanced classification problems like fraud, where maybe only 0.1%, 0.2% of transactions are actually fraudulent.
Tiny fraction.
Exactly. Accuracy is almost useless. Think about it. A model that just predicts not fraud for every single transaction could easily achieve over 99% accuracy.
Wow. Okay, yeah, that would be completely useless for catching fraud.
Total useless. So we have to shift our focus dramatically. We look at metrics that evaluate performance specifically on that tiny minority class, the fraud itself. Things like precision. That minimizes false positives, flagging good transactions as bad. Crucial for customer experience, right? You don't want to block legitimate purchases.
Definitely not. Very annoying for customers.
Then there's recall, sometimes called sensitivity. That minimizes false negatives, missing actual fraud. Crucial for preventing financial loss.
Okay, precision versus recall, the classic trade-off.
It is. And the F1 score tries to balance both. But the most important metric, especially for imbalanced classification, is the area under the precision recall curve, or AUPRC.
AUPRC, why is that the key one?
Think of AUPRC as the ultimate report card for a fraud model. It effectively summarizes the precision recall trade-off across all possible decision thresholds without being fooled or skewed by that massive number of legitimate transactions. It gives you a much truer picture of performance on the thing you actually care about catching fraud without too many false alarms.
Gotcha. So these technical terms, precision recall, AUPRC, how do they translate into actual business impact?
They translate directly into costs and consequences. For instance, a false positive flagging a good customer's transaction leads to a poor customer experience. Maybe they abandon their purchase, maybe they complain. Plus, it costs money for manual review and it can damage your reputation.
Right.
A false negative letting fraud slip through means direct financial loss. It erodes customer trust if their account gets hit. And it can even lead to regulatory scrutiny if it happens too often.
So finding the right balance is key.
Absolutely. And that optimal balance between catching fraud, recall, and avoiding false alarms, precision, that depends entirely on the business's specific risk appetite. It's fundamentally a business decision guided by the model's performance metrics.
That makes perfect sense. It's not just a technical dial to turn.
Not at all.
So, okay, we've defined the problem, checked feasibility, figured out how to measure success. That blueprint phase sounds incredibly thorough. It makes me wonder, how do you visualize the entire system before you actually start building? What does that high-level architecture look like?
Yeah, great question. That's where the high-level system architecture design comes in. For a real-time AI solution like this, you typically design it using a microservices-based approach.
Microservices, why?
It ensures scalability, reliability, and maintainability. Each part does its job independently, so you'd map out the key components.
Like what?
You'd have a data ingestion layer, maybe using something like Apache Kafka, to handle that high-throughput stream of real-time transaction events.
Okay, getting the data in.
Then a dedicated feature engineering service. Its job is to take those raw transactions and enrich them, create those smarter features we talked about earlier.
The behavioral and temporal features.
Exactly. Then, offline, you need a model training pipeline. This runs periodically, maybe daily, maybe weekly, to retrain the model on fresh data. And a model registry to keep track of all your model versions.
Version control for models, essentially.
Precisely. Then the star of the real-time show, the inference service. Often built with something fast like FastAPI, it exposes a REST API that other systems can call to get a fraud prediction in milliseconds.
The thing that actually makes the prediction.
That's the one. And finally, you absolutely need robust monitoring and alerting systems. Think Prometheus and Grafana, perhaps. These are your eyes and ears on the system's health and performance 24/7.
So you know if things are working or if the model's performance is degrading.
Exactly. It ensures the system stays reliable and effective. That whole picture is sketched out before the main build starts.
Okay, with that meticulous blueprint finally in hand, we're ready to move into the build phase. Now, I've heard that old saying, garbage in, garbage out, is like 10 times truer in machine learning.
Oh, absolutely. Maybe 100 times truer.
So what's the very first thing you tackle on the data side to make sure you're not feeding the model garbage?
You hit the nail on the head. The first step is building a really robust data pipeline. That starts with just loading the data and doing what's called exploratory data analysis, or EDA.
EDA, what does that involve?
It's where you really dig in and get to know your data. You look at distributions, find missing values, outliers, and crucially, in fraud, you uncover characteristics like that severe class imbalance we discussed.
Finding that 0.172% fraud rate, for instance.
Exactly. Seeing that number pop out of your EDA is critical. If you don't understand that imbalance right from the start, your model is basically doomed before you even train it. It'll just learn to say, not fraud all the time.
Right. So beyond just cleaning up the data, handling missing values and stuff, how do you make it, well, smarter for the model? You mentioned feature engineering before. What kind of predictive signals are you really looking for in fraud cases?
Yeah, feature engineering is where a lot of the magic happens. It's about creating new, more informative features from the raw data you have. Essentially, you're giving the model better ingredients to work with.
Making its job easier.
Precisely. For fraud, temporal features are often incredibly powerful. Like simply transforming the transaction timestamp into hour of day can be very predictive. Why? Because fraud often peaks at weird, non-standard hours when legitimate activity is lower.
Ah, interesting, like 3 a.m. transactions.
Exactly. Or behavioral features. These track patterns for a specific card or user. Things like calculating the average transaction amount over the last 24 hours for that card, or the time elapsed since the last transaction from that card.
Okay, looking for deviations from normal behavior.
That's the key. Sudden spikes in spending, transactions happening much faster than usual, unusual locations. These deviations from established normal patterns are often strong, subtle indicators of fraud that the raw data alone might not reveal so clearly.
Got it. Now let's go back to that tiny sliver of fraud data, less than 0.2%. That's a huge imbalance. How do you handle that technically without just biasing the model heavily towards the majority class, or worse, accidentally cheating by leaking information from the test set?
This is a really critical challenge in fraud detection, and many other domains too. A very effective technique we use is called SMOTE.
SMOTE. What's that stand for?
Synthetic Minority Oversampling Technique.
Okay, sounds fancy. How does it work?
Basically, it creates new synthetic examples of the minority class, in our case, fraudulent transactions. It does this intelligently by looking at existing fraud examples and creating new ones that are similar but not identical, kind of interpolating between them in feature space.
So you're generating more fraud examples to balance things out.
Exactly. But here's the absolutely crucial part, the common pitfall you mentioned. It tripped up even experienced teams sometimes.
Okay, what is it?
You must apply SMOTE only to the training data after you've split your data set into training and testing sets.
Only on the training data. Why is that so important?
Because if you apply SMOTE to the entire data set before splitting, your testing set will contain synthetic samples that are derived from information also present in your training set.
Ah, data leakage.
Precisely. It leads to data leakage. Your model will look fantastic during evaluation because it's essentially seen variations of the test data during training. Its performance metrics will be unrealistically inflated.
So it seems like a superstar in testing.
But then it crumbles when it sees truly new, unseen data in the real world. So split first, then apply SMOT only to the training portion. That ensures your evaluation is valid and reflects true generalization performance.
That's a super important practical tip. Okay, so data is loaded, cleaned, engineered, balanced with Stephanie correctly.
Yeah.
Now we actually build the model. What types of models are you typically looking at for fraud detection? And how do you structure them to fit into something like LangChain, which people often associate more with LLMs?
Good question. For model selection, it's good practice to start with a simple, interpretable baseline model, something like logistic regression.
Just to get a benchmark.
Exactly. See how a basic approach performs. Then you move to more advanced high-performance models. For fraud on tabular data, like transaction records, gradient boosting machines are usually state-of-the-art. LightGBM is a particularly strong choice.
Why LightGBM specifically?
It's incredibly efficient, fast training times, lower memory usage, and it generally provides excellent accuracy on structured tabular data. Speed and accuracy are paramount for real-time fraud detection.
Makes sense. And the LangChain part, how does a traditional ML model like LightGBM fit in there?
Yeah, that's interesting. While LangChain is famous for orchestrating LLMs, its core concepts, especially the LangChain Expression Language, or LCEL, are really flexible.
LCEL.
You can absolutely structure traditional ML models using LCEL. The key is to wrap your model's prediction function, the part that takes input features and outputs a fraud probability inside a runnable lambda.
Oh, runnable lambda. Okay.
This makes your LightGBM model or any other ML model behave like any other LangChain component. It becomes part of a chain.
What's the benefit of doing that?
Modularity and extensibility. It makes the whole system much cleaner. For example, imagine down the line you want to add a step after the fraud prediction. Maybe use an LLM to generate a human-readable explanation for why a transaction was flagged.
Ah, so the analyst gets not just a score, but a sentence explaining it.
Exactly.
Yeah.
Because you've wrapped your LightGBM model in a runnable, plugging in that LLM explanation step becomes much easier within the LCEL framework. It keeps the system adaptable for future enhancements.
Very cool. So the model is trained, maybe wrapped in LangChain, but it's still just code, maybe in a notebook. As you said, it provides zero business value sitting there. How do you get this thing out into the real world, actually patching fraud in real time as a robust, scalable service?
Right, deployment. This is where the rubber meets the road. You absolutely need a real-time inference API. A way for other systems like the transaction processing system to send data and get a prediction back fast.
And what do you use for that API?
FastAPI is an excellent choice, a really popular Python framework for this.
Why FastAPI?
Its asynchronous capabilities mean it's built for speed and can handle a huge volume of simultaneous requests for predictions without getting bogged down. That's critical for real time. Plus, it automatically generates interactive API documentation, like Swagger UI.
Oh, that's handy for developers using the API.
Hugely handy. It makes integration much easier. But if you're already using LangChain, like we discussed, there's an even more integrated approach, LangServe.
LangServe, part of the LangChain ecosystem.
Exactly. LangServe is specifically designed to take any LangChain runnable, including our fraud detection chain with the wrapped LightGBM model, and instantly deploy it as a REST API.
Instantly. That sounds easy.
It simplifies the process considerably. With just a few lines of code, LangServe spins up an API server based on FastAPI, actually. And it automatically gives you useful endpoints like invoke to send data and get predictions, and even an interactive playground interface for testing right in your browser.
Okay, so LangServe builds on FastAPI, but makes it even easier for LangChain objects.
Pretty much, yeah. Streamlines the deployment of chains.
Now, one headache I always hear about is making sure the application runs the same everywhere, on the developer's laptop, on the test server, in production. How do you solve that classic "it works on my machine" problem? You mentioned containerization with Docker earlier.
Ah, yes, Docker. It's absolutely essential for reliable deployment in modern systems.
What exactly does it do?
Docker packages your application code, your Python scripts, your train model file, everything along with all of its dependencies. That means the specific Python version, all the libraries like LightGBM, FastAPI, LangChain, even system tools. Everything needed to run.
All bundled together.
Exactly.
Yep.
Into a single isolated portable unit called a container image. This container runs identically regardless of the underlying machine.
So it creates a consistent environment.
Precisely. It completely eliminates those "it works on my machine" nightmares because the environment is the same everywhere. You define this environment using a Docker file and list dependencies in a requirements.txt file, and Docker builds the image. Deployment becomes much, much simpler and more reliable. It's like putting your entire app with its own little operating system into a neat, standardized shippable box.
That sounds incredibly useful. Okay, so you've containerized the fraud detection service with Docker. How does this neat little box actually live and scale up in the cloud to handle potentially millions of transactions?
Right, getting it into the cloud. Once you have that Docker image, you first push it to a container registry. Think of it like a central storage place for your Docker images. Amazon ECR, Elastic Container Registry, is a common one if you're using AWS.
Okay, image stored. Then?
Then, cloud platforms designed for machine learning, like Amazon SageMaker, can take over. The high-level workflow usually involves a few steps. First, you create a SageMaker model entity that points to your Docker image stored in ECR.
Telling SageMaker where the code lives.
Yep. Second, you define an endpoint configuration. This specifies the infrastructure details, like what kind of virtual machine instances to run the container on, how many initial instances you want, etc.
Setting up the servers.
Essentially, yeah. And finally, you create the SageMaker endpoint itself using that configuration. SageMaker then pulls your Docker image, launches it on the specified instances, and exposes it as a secure, scalable HTTPS endpoint.
And SageMaker handles the hard parts.
That's the beauty of it. SageMaker manages all the underlying complexities, setting up load balancers to distribute incoming prediction requests, automatically scaling the number of instances up or down based on traffic, performing health checks to replace unhealthy instances, all that operational heavy lifting so your team can focus on the model and the application logic.
That's a huge advantage.
It really is. And the power of containerization with Docker shines here too. That same Docker image you built. With very minimal changes, mostly just configuration, you could deploy it to other major cloud platforms like Microsoft Azure Machine Learning or Google Cloud Vertex AI.
So high portability. You're not locked into one cloud provider.
Exactly. Containerization gives you that flexibility, which is incredibly valuable.
Okay, fantastic. So we've meticulously planned with the blueprint, done the hard work in the build phase, containerized it, and deployed it to the cloud using something like SageMaker. It's live, catching fraud. Are we done? Can we finally put our feet up?
If only. Deployment is absolutely a huge milestone, definitely worth celebrating. But it is not the finish line. Not even close, really.
Okay. So what comes next?
What comes next is the feedback loop phase. This is absolutely critical because model performance isn't static. It can, and often does, degrade over time.
Degrade. Why would it do that?
Because the world changes. This is something called concept drift. The underlying patterns of fraud attacks evolve. Criminals get smarter. Legitimate customer behavior might also change over time. If your model is trained on historical data, it might become less effective as these patterns shift.
So the model gets stale.
Essentially, yes. That's why continuous evaluation, ongoing monitoring, and digging into why the model makes certain decisions, interpretability, are absolutely essential. They ensure the system remains reliable and effective in the long run. Think of it as ongoing maintenance and evolution to keep it performing at its peak.
Right, makes sense. Now, earlier, you really hammered home that standard accuracy is misleading for fraud detection. So after deployment, in this feedback loop phase, what's the right way to evaluate how the model is actually performing in the wild? Especially considering that crucial trade-off between catching fraud and avoiding false alarms.
Yeah, we keep coming back to the precision recall PR curve. Post-deployment, this is still your go-to tool.
The PR curve again. Remind me why it's better than, say, the ROC curve here.
Because the PR curve focuses directly on the performance for the positive class, the fraud cases, which are rare. It's not skewed or overly optimistic due to the vast number of easy-to-classify true negatives, legitimate transactions, which is what happens with the ROC curve in highly imbalanced scenarios. The PR curve gives you a much more honest assessment of how well you're doing on the actual problem you care about.
Okay, more honest for imbalanced data.
Exactly. And crucially, the PR curve enables that vital business impact analysis we talked about. You look at the curve and say, okay, currently our decision threshold gives us X% recall, we're catching this much fraud, but it comes at the cost of Y% precision, meaning this many false positives.
Translating the curve into real numbers.
Precisely. You can then ask the business stakeholders, if we adjust the threshold to catch 90% of fraud, increase recall, our precision might drop to 75%. That means for every 100 transactions we flag, 25 will be legitimate customers inconvenienced, costing us zillidity and manual review. Is that acceptable?
So it directly connects the model's technical performance to the business consequences.
Yes. It makes the trade-offs explicit and allows for informed decisions about where on that curve the business wants the model to operate.
That's powerful. Now, in high-stakes areas like fraud or maybe even healthcare, just getting a yes or no from the AI, a black box prediction often isn't good enough, right? You really understand why. How do you tackle that? How do you make the AI explain itself?
That's a huge area, model interpretability. And you're right, it's crucial for building trust, for debugging, and for regulatory compliance in many cases. Tools like SHAP are invaluable here.
SHAP, what is that?
It stands for Shapley Additive Explanations. It's a technique based on concepts from game theory, believe it or not.
Game theory for AI explainability.
Yeah. Essentially, SHAP calculates the contribution of each input feature, like transaction amount, time of day, location to a specific prediction. It tells you how much each factor pushed the prediction towards fraud or not fraud.
So it breaks down the reasoning for a single prediction.
Exactly. It acts like a forensic investigator for your model's decisions. Instead of just a score, it shows you the why. We often distinguish between two types of interpretability with SHAP.
Okay.
There's global interpretability. You use something like a SHP summary plot. This shows you which features are the most important overall across the entire data set, like maybe time since last transaction is consistently a top driver of fraud predictions.
Seeing the big picture trends.
Right. But then there's local interpretability, which is often even more powerful for fraud analysts. You use a SAP force plot. This explains exactly how each feature contributed to one single specific prediction.
For that one transaction that got flagged.
Exactly. The analyst reviewing the alert can see, okay, this was flagged mainly because the amount was unusually high for this card, and the transaction occurred far from the user's normal location. It helps them quickly validate or dismiss the alert and builds immense confidence in the system.
That transparency must be crucial for adoption.
Absolutely fundamental.
Okay, so we can evaluate performance with PR curves, explain individual decisions with SAP. What about monitoring the entire system, debugging when things go wrong, and ensuring that continuous improvement actually happens over the long haul?
This is where observability and debugging tools come into play. And something like LangSmith fits in really well, especially if you've used LangChain LangServe.
How does LangSmith help here?
Because we use LangServe to deploy our API, it's automatically instrumented for LangSmith tracing. This means every time a prediction request comes in, LangSmith logs detailed step-by-step information about how that request was processed through our chain.
Like a detailed log of everything that happened.
Exactly. You can see the inputs, the outputs to the feature engineering step, the input to the light GBM model, the final prediction, everything. If something goes wrong, or you get an unexpected result, you can trace it back step by step to pinpoint the issue. It makes debugging much, much faster.
That sounds incredibly useful for troubleshooting.
It is. But there's another powerful feature relevant to the feedback loop, curating datasets from production traces.
Curating datasets. How?
Let's say you observe a problematic transaction in LangSmith. Maybe it was a false positive that really annoyed a VIP customer. Or maybe it was a clever new type of fraud that the model missed a false negative.
Okay, real wind edge cases.
Exactly. You can select that specific trace in LangSmith, the inputs, the outputs, the whole execution path, and save it directly to a dataset.
Building a library of tricky examples.
Precisely. This curated dataset becomes invaluable for regression testing. When you train a new version of your fraud model, you systematically test it against these known, real-world edge cases and failures.
To make sure the new model handles them correctly.
Yes. It ensures that your model improvements are actually addressing past weaknesses and adapting to new challenges seen in production. It forms this really robust feedback loop where monitoring directly fuels continuous improvement. It's how the system learns and stays effective over time as the world changes around it.
Wow, what a journey. We've really gone end to end there. From meticulously framing that initial business problem all the way through building, deploying, and now continuously monitoring and improving a real-time AI solution.
It's quite the process.
And it's absolutely clear the deployment, as you said, isn't the finish line. It's really just a significant milestone on what seems like an ongoing path.
Exactly. That's the core takeaway, I think. Building a truly production-grade AI solution isn't a one-shot deal. It's a continuous, iterative cycle.
Always learning, always improving.
Precisely. The insights you gain from monitoring how the deployed model performs, from understanding its failures using tools like SHAP and LangSmith, and from gathering feedback from the actual users and stakeholders, those insights are the very inputs that fuel the next iteration of the whole development lifecycle. It's never truly done.
That really clarifies the whole picture. It's not just about the algorithm, but the entire system and process around it.
Couldn't have said it better myself.
So for you, our listener, here's a final provocative thought to chew on as we wrap up. What black boxes or complex problems exist in your own world, maybe at work, maybe somewhere else, that could benefit from this kind of structured end-to-end thinking? And if you applied it, what new insights might that transparency and that continuous feedback loop actually reveal?